some fuckers. So today we actually have kind of a challenging problem. So we supposed to find all integers a and m bigger than 1, positive integers a and m bigger than 1, such that a to the power of m minus 1 is prime. So what do we do with this? Well, what can we do with this? We can use a geometric sum. So we can say that a to the power of m minus 1 is equal to a times 1 times 1 plus a squared plus everything up to a to the power of m minus 1. Or we can also write this as a times a minus 1 times the sum where k goes from 0 to m minus 1 of a to the power of k. So now let's think. A prime number. Because we're dealing with integers, right? Then we can use prime factorization. Yes. So we know that if something is a prime, and this something can also be written as a product of two things, what do we know about these products? They have to be the prime and 1. Because if a number can be written as a product of two numbers, which none of them are 1, then it's not a prime by definition. So one of them has to be 1 and the other one is prime. So we have case 1, which is that a minus 1 is equal to 1, which gives that a is equal to 2. Or sorry, we'll start with the other case. So, case 1. The sum is equal to 0. The sum is equal to 1. I'll just write it out like this. The sum is equal to 1. So, when is this sum equal to 1? Well, we can have that. Well, actually, there are no cases when a and m are bigger than 1. Because if am is bigger than 1, then that means that this is bigger than 0, which means it is 1 or bigger. So we at utmost least, we have 2, the sum of where k goes from 0 to 1. Yes. And a has, the smallest a can be is 2. So we have 2 to the power of 0, which is 1, plus 2 to the power of 1, which is 2. So the sum is 3. So this can never hold. This can never hold. So case 2 is the more complicated one, where, as I said before, a minus 1 is equal to 1. So that means that a is equal to 2. So now we rewrite the problem as 2 to the power of m. Yes, so now we rewrite the problem as 2 to the power of m minus 1 is, I'll just write it like this, is some prime p. So, okay, we know that 2a has to be 2, because this couldn't be the case, and these are the only two cases. So now we have a much simpler problem. Not a lot simpler, but still. So now we think about this. So Now, if we go do this procedure again, we will just get 1 times this thing. So yeah, we know we're good. As long as we can't describe this in some other way. If m, let's say that m is non-prime, meaning that we can write m as some, maybe I'll denote this as c times k, then we can rewrite this as 2 to the power of c times k minus 1, which is equal to 2 times to the power of c to the power of k minus 1. And this, as we know, we can do this procedure again. So this is equal to 2 to the power of c minus 1 times the sum where, okay, now we don't use k, let's use I, goes from 0 to k minus 1 of, uh, well, yeah, 2 to the power of c to the power of I. So, and if this is the case, then we have the same thing again. This has to be prime. So either this is 1, which means that c is 1 and m is just equal to k. Well, exactly, c has to be 1, which means that m can only be written as 1 times k, and then m meaning that m is prime. So that's our like version of case 2 here, but our version of k1 here gets a bit more complicated. Yes, so it's almost the same thing here, because if, yeah, and both of these are integers, of course. Um, so if this is supposed to be equal to 1, we know that 2 to the power of c to some integer c can only be 1 when I is 0 and only when I is 0. So meaning that I is 0, that means that that's the only sum we can get. So therefore it has to range from 0 to 0, meaning that k minus 1 is equal to 0, which means that k is equal to 1. And then we arrive at the same thing as before. If we can only write m as c times 1, then m and c are the same, and they have to be prime. So so our solution now is, well, yeah, first case one didn't work at all. So then we have that a is 2, and what we proved here is that m has to be also has to be prime. So our solution is 2, a is equal to 2, and m is prime. And then we must have a prime, and it's the only case where we have a prime actually. So yeah, that was it's a bit trickier. I get it if you didn't really follow along. I'm running out of chalk also, so I didn't feel like writing. I didn't want to write anything more. But well, yeah, that was basically everything. So I'll see you some other time. Bye bye.